time for the big one, Jupiter. Now Jupiter is big. That's kind of the deal, and well named Jupiter, like the king of the planets, right? Well named. They named it Jupiter years, thousands of years before we discovered that it was the largest planet. Okay, so well named. Let's take a look at some vital stats here for our man Jupiter. Semi-major axis is 5.2 AU. So a lot further out from the sun, 5.2 times further out from the sun than we are. Not much light out there. You're getting pretty far out. The orbital period, 11.9 Earth years. So think of yourself 12 years ago. What were you doing 12 years ago? Well, it took from then until now for Jupiter to make one path around the sky. One trip around the sun. Let's see, rotational period. This is a nice one. This is one we're going to be looking at. 0.41 Earth days. That's less than 10 hours. Think about it. Our dear planet rotates once every almost 24 hours, right? And we here in Atlanta, we're going about 1,000 miles per hour around the center of the Earth to make it around once in a day. So our period is 24 hours, roughly. And we're going roughly 1,000 miles an hour here at the latitude of Atlanta to make it around once. Well, Jupiter is way, way, way bigger than the Earth, as we'll see, way bigger, but it only takes about less than 10 hours to make one rotation. It is the fastest rotating of all the planets and the largest, which is weird. Okay, it really goes fast. Its mass is 300, we've known this number for a long time, 318 times the mass of the Earth. So if you wanted to put Jupiter on a scale and balance it with Earths, you'd have to put 318 Earths on one side of the scale to balance out a single Jupiter. In fact, the mass of Jupiter is more than twice all the other planets combined. So if you want to think about the solar system in the simplest possible way, it's basically the Sun and Jupiter. That's basically it. And then all the rest. But even so, the Sun is 1,000 times more massive than Jupiter. So, and the Sun, as we will see later on, is just an average sized star. So the radius is 11.2 Earth radii. That's a little more than 10, but you think roughly you can put, I think in terms of 10. It's really 11.2, but you can put roughly 10 Earths across the face of Jupiter. Okay, stick with me here. We're going someplace. You can put roughly 10 Earths across the face of Jupiter, and you can put roughly 10 Jupiters across the face of the Sun. Okay, so the Earth is to Jupiter roughly in size as Jupiter is to the Sun in size. Roughly a factor of 10. A little bit over 10 in both cases, but the comparison's pretty good. So the Earth is to the Jupiter in size as Jupiter is to the Sun in size. Number of moons. Here's a doozy. We already mentioned this before, several lectures ago, but I think the number is 79. At least it was when our class started. It might be up into the 80s by now. I have to go check Wikipedia to find out. 79. The density, now this is also an interesting number, is 1,300. This is way lower, super way lower than all the planets we've seen before. Mercury, Venus, Earth, all well over 5,000. Mars was less, it was 3,900, but this is totally different. 1,300 kilograms per meter cubed. Okay, that's really light. That's only slightly more dense than water. Slightly. Okay. Obliquity, that is the axial tilt, is nothing to write home about, 3.1 degrees. So its tilt is very mild. It really doesn't have any seasons to speak of at all, unlike Mars and the Earth. The magnetic field is something to write home about. It is 14 times the magnetic field of the Earth. That's huge. The Earth has a very large magnetic field, unusually large for in terrestrial planets. Good thing for us as living systems, right? Remember how I told you that the magnetic field keeps us from being swamped by solar wind, fast-moving protons and electrons. But the magnetic field of Jupiter as a whole is in a class by itself. Eccentricity of Jupiter is 0.049, which is bigger than the Earth's, less than Mars's, and not going to be real important for us. Surface temperature is cold, 165 kelvins, which is equal to about negative 163 degrees Fahrenheit. As we go out into the outer reaches of the solar system, we'll see that the temperatures of planets gets colder and colder, and this Kelvin number here will get closer and closer to absolute zero. It gets very cold, not even close to absolute zero, but they'll get lower and lower, going towards that number, never going negative. So those are the vital stats. I do want to make this point here clear also. This is important. Notice that the atmosphere of Jupiter is very different from what we've seen for Venus and for Mars and for the Earth. I didn't mention it, but you read about it. Mars's atmosphere is pretty thin, mostly CO2. And that way it's similar to Venus's. It's mostly CO2 also, but it's super thin, about 10,000 times less dense than Venus's, about 1/100th the density of our atmosphere. But there is no hydrogen or helium in the atmospheres of the inner planets. None. In our atmosphere, there's no hydrogen, H2, and there's no helium. We'll see why later on. We'll do a lab, I think, next week. No, later this week we'll do a lab to see why that is, why there is no hydrogen or helium in the inner solar system, but there's lots of it in the outer solar system. In fact, all the big gas giants, Jupiter, Saturn, Uranus, Neptune, all are predominantly hydrogen with a really good dose of helium thrown in. Okay, so that is the composition, and it's very different. That's gas. Okay. And before I talk about the rotation rate, I want to say one last thing, which is this. Talk about this density. Here. There is no surface of Jupiter. I made this point before when we contrasted the terrestrial and the Jovian planets. There is no surface. Okay. If you go jump on Jupiter, you'll just fall through the atmosphere. It'll get progressively thicker and thicker and hotter and hotter and hotter, and there probably is a solid core somewhere down there, but the transition is not a clean one. From fluid to solid is not it's a very gradual transition, and you can't go walking around on the surface down there. It's much too hot. You would melt long before you got down there. There may be a rocky core at the middle of Jupiter, but it's best to think of it just as a big ball of gas. Okay, where you can't go walking upon it. So if you look at a picture of Jupiter, it looks something like this. Okay. Number one, it's nice and spherical. But what you get is you get these stripes, right? These regions where it's a little dark. It's a stripe planet. Unlike all the other ones, it has a different look to it, right? It has these regions where it's dark, regions where it's light. So dark, light. Where I'm doing the cross hatching here are the light regions. Right. You have these bands, maybe a really thin light region here. And then you have down in the southern part, you have this thing called the Great Red Spot, which is, I've exaggerated the size of it here relative to the rest of the planet, but you can fit 2 or 3 Earths across the Great Red Spot. And it happens to be at the boundary between a dark region and a light region. If you look, sort of step back and look, you'll see that it does fall between a couple of these regions here. So this is more or less what Jupiter looks like. Okay, there's these bands parallel to the equator. Okay, and then there's this thing called the Great Red Spot. Now, believe it or not, the light parts are called zones. How's that for a clever name? And the dark regions, the dark sections, are called belts. And of course we have the great red spot right there. So there are names for these. The belts are regions of low pressure. You know, on the Earth, there are regions of high pressure, regions of low pressure, which give rise to weather patterns, right? If you look at any weather map, you'll see little H's and little P's. H's and L's around a weather map, right? Those are what give rise to the weather. Without those high and low pressure regions, there is no interesting weather to speak of. It is those that bring in storms. It's those that bring in hurricanes. Like a really low pressure area will bring in a hurricane. Well, it turns out that zones, which are the light colored stripes across Jupiter, and the belts, which are the dark colored stripes across Jupiter, are regions of high pressure and low pressure, respectively. But unlike the Earth, they're all kind of stretched out into these stripes that go all the way around the planet. They're not, on the Earth, they're more spotty, right? They sort of appear everywhere. They're not stretched out in these nice organized paths like they are on the planet Jupiter. And they are stretched out this way. These are basically weather patterns on Jupiter. And they're stretched out this way because of the high rotation rate. Remember how quickly Jupiter is rotating. Extremely fast, less than 10 hours for one loop around. I don't do the math, but I can tell you it's tens and tens of thousands of miles per hour. It's at any point on this, it's rotating, going very fast. And that basically takes these weather patterns and stretches them out into these bands. So if we could get the Earth and make it spin like nearly as fast, those low and high pressure regions would also organize themselves in a similar way. So it's because of the very quick rotation that's happening. And there are storms happening everywhere. In fact, the Great Red Spot is just a big storm. It's persisted now for 400 years, but it's a storm. And there are other storms that you see. If you look closely, you'll see there are little smaller regions. They're not dark red like that. You'll see, usually not in the belts like that. Usually they're on the boundaries between belts and zones. But you see smaller storms. Okay. And those are known as, get this, you ready for some really interesting titles? There's these things called brown ovals. I'm not making this up. This is what scientists call them. Brown ovals and white ovals. Okay, so those are features of Jupiter's atmosphere as well. But basically, they're little storms. The brown ovals are actually openings where you can see down into deeper layers of the atmosphere. The white ovals are actually storms. So make that clear. Brown ovals are not storms. White ovals are also storms, just like the Great Red Spot is. Okay. They show up everywhere. So that's all I'm going to say about Jupiter for right now. We're going to talk next about its moons. So we already sort of covered this high rotation rate. Business, where'd it go? This here, that was kind of one of our interesting numbers, right? It takes these weather patterns and spins them out into these zones and belts like this. The next number we're going to look at is this baby right here, because that's a lot of moons. We're going to look at its four most famous coming up next.